Welcome to this technical video, which describes the potential issues related to feed pump design for high-pressure pump systems. The video explains the background and issues arising from gas bubbles in feed water and feed pump cavitation. It also explains different ways to prevent gas bubbles and thereby preserve the surface life of high-pressure pumps. Some of the slides contain speak, so please turn the sound on. Let's get going. You can always pause and rewind the video if you need more time for reading a slide. In high-pressure pump systems, the feed pump increases the water pressure to the level required to run the high-pressure pump. If the inlet pressure of the high-pressure pump is too low, the high-pressure pump may cavitate. Cavitation is a serious problem, causing downtime and increasing the need for service. Worst case, cavitation may reduce the surface life of the pump. Typical pressure losses that need to be compensated are pressure drops in the filter, piping, valves, and instrumentation such as flow meters. This is a simplified drawing of a feed pump system where we have left out instrumentation and valves. Let's take a closer look at the critical elements of the system. The design of the tank is important, as is the feed pump turn-down ratio. Both parameters are important for optimum operation and to avoid gas bubbles in the feed water. The pump used here is a single-stage centrifugal pump, a pump type that may cause problems with gas bubbles. It is important that the high-pressure pump pre-filter is a 10 micrometer absolute filter. The graph shows the concentration of dissolved gases as a function of the water temperature. You can see that the concentration of dissolved gases drops as the water temperature increases. The pressure also affects the concentration of dissolved gases. The values in the graph are based on an ambient pressure of 1 atmosphere. As long as the gases are dissolved, they do not cause problems. The graph shows the relation between vapor pressure and water temperature. Pressure is measured in kilopascal, temperature in degrees Celsius. If the pressure drops below the water's vapor pressure, the water will change from liquid to vapor. Raising the pressure above the vapor pressure will reverse the process. As soon as the water turns into steam, the dissolved gases turn into free gases or small gas bubbles. In order to transform the free gases back into dissolved gases, the water temperature must be lowered and the water flow in the piping must be low, a costly and difficult process. Therefore, it is important to prevent gas bubbles in the first place. Over time, gas bubbles cause serious damage to the high-pressure pump. This means that the pumps may require more frequent service. Worst case, the service life of the high-pressure pump is threatened. Why do the gas bubbles cause problems to the high-pressure pump, you may ask? Here is the answer. The gas bubbles alter the compressibility of the water, and high-pressure pumps, also known as positive displacement pumps or axial piston pumps, are designed for non-compressible fluids. The increased compressibility especially affects the decompression cycle of an axial piston pump. The gas bubbles prevent a complete decompression of the piston. As soon as the piston gets in contact with the suction port, the energy stored in the water will be released in the form of a jet. This jet will erode material on bushing and piston slippers. And cause gas bubbles in the water. Take your time and read through before we look at some of them in more detail. The inlet of water to the tank is very important. If the inlet is too close to the pump suction port, the air bubbles generated by the splash are drawn into the pump. This phenomenon is most likely to occur when the water level of the tank is low. The most obvious solution is to move the tank inlet away from the pump inlet, but this only helps if you can keep the water level sufficiently high. As soon as the water level drops to a certain critical point, the water splashes will entrap air in the water flow and then enter the feed pump. Another solution is to divide the tank by a baffler plate that enables the release of gas bubbles before the water enters the pump. Here, you can see a system with a vortex that generates air which enters the feed pump. A vortex is a swirl, like the one you see in your bathtub when the bathtub is almost empty. If you look closely at the swirl, you can see that the swirl draws air into the water flow. There are several tank or pump inlet designs that prevent vortex from occurring in the tank. The simplest is the vortex breaker, which can be seen on the next slide. Now that we have described some of the tank design parameters that may cause gas bubbles, it is time to learn a bit more about the operation of the centrifugal pump. A centrifugal pump is typically used as feed pump for the high-pressure pump. The top graph illustrates a flow curve. It shows the relation between flow demand and pump outlet pressure for a centrifugal pump at fixed speed. The next graph shows the net positive suction head required, a highly significant parameter for optimum operation of the feed pump. The pressure scale for NPSHR is typically absolute pressure. Please note that the NPSHR curve will increase until the maximum flow is reached. Exceeding the max flow rating for the pump will cause the NPSHR value to increase exponentially. Operation under such conditions is likely to cause pump cavitation. In this slide, we take a look at the relation between the flow demand of the high-pressure pump, the feed pump outlet pressure, and the net positive suction head required. The vertical red dotted line represents the flow demand of the high-pressure pump. The point where the orange curve and the red dotted curve cross represents the outlet pressure of the centrifugal pump. The crossing between the black NPSHR curve and the red dotted line represents the required inlet pressure for the centrifugal pump. In order to get the full understanding of this, we need to take a closer look at the meaning of NPSHR and NPSHA. As already explained, the NPSHR is the required minimum inlet pressure of a centrifugal pump, whereas the net positive suction head available, NPSHA, defines the available inlet pressure on the pump port. The NPSHA value is typically affected by the water level in the tank, pressure drop in valves and piping, and a safety factor for turbulent flow conditions at the pump inlet. Please note that the NPSHA curve reflects a water tank where the water level is constant. A drop in the water level will also affect the NPSHA value. This is highly critical and may cause cavitation of the centrifugal pump. This slide helps you design the correct feed pump setup by showing 3 different scenarios. The first one, according to the book, the next, a critical design that may cause problems, and last, a no-go design that is almost certain to cause serious cavitation. In the first scenario, the safety margin is sufficient over the full flow range, but still, you have to take into account variations of the water level in the tank when designing the system. In the second scenario, the NPSHA is sufficient over a wide range of the pump's flow output, but when the flow becomes high, the NPSHA value becomes critical and may cause the centrifugal pump to cavitate. The third scenario shows a system with a very low available net positive suction head. The pump is likely to cavitate at most flow levels. Cavitation of the feed pump is always critical and may potentially damage the high-pressure pump. The graph explains the consequences of operating a centrifugal pump outside the pump's best efficiency point, BEP. Operating the centrifugal pump at low and high flows may cause cavitation, which affects the service intervals of the high-pressure piston pumps. This is due to the fact that the centrifugal pump under these conditions will release gas bubbles into the water feeding the high-pressure pumps. Therefore, it is important to avoid the high and low flow operational areas in order to protect both the low-pressure feed pump and the high-pressure pump. As already mentioned, low and high flow cavitation in the centrifugal pump may affect service intervals and service life for both feed and high-pressure pumps. Unfortunately, there is no exact definition of when the gas bubbles start to form. It is a gradual process, starting before the defined cavitation zones at high and low pressures. Now it is time to take a closer look at the actual cavitation process. As soon as the liquid pressure inside the centrifugal pump crosses the vapor pressure curve, the liquid will change to gas. The gas bubbles will then travel inside the pump until they enter a zone with higher pressure. When the gas bubbles enter the high pressure zone, the bubbles start to implode. The implosion generates a jet with a force of several thousand bar, which will erode material from the internal parts of the pump. Especially the impellers of the centrifugal pump are exposed to cavitation and should be inspected carefully. The problem then moves on to the high-pressure pumps. As the water enters its vapor phase, the dissolved gases will enter their gaseous form and form gas bubbles, which will travel towards the high-pressure pumps. There can also be other reasons for cavitation that you need to look out for. For instance, Cavitation can occur at pressures much higher than the liquid vapor pressure. This is typically related to very high flow velocities inside the pump. In this case, the high-speed flow may create zones of low pressure inside the pump. The pressure in these zones is lower than the vapor pressure and may cause bubbles to form. In this slide, you see three different pictures that explain cavitation inside a single-stage centrifugal pump. In the upper left corner is an example of the basic design of a centrifugal pump. Liquid entering the pump through the inlet port is accelerated by the impeller, especially at the peripheries, where pressure builds up before the outlet port. The picture to the right shows a typical cavitation. Cavitation typically occurs in the low pressure zones, and gas bubbles will be pushed towards the periphery of the impeller towards the high pressure zone. In some places, along the surface of the impeller, the surrounding pressure will be so high that the gas bubbles collapse. This is where the material erosion occurs. The picture at the bottom of the slide shows an impeller from a centrifugal pump that has been exposed to cavitation. As you can see, the cavitation erodes the metal. The performance is evidently low with this kind of impeller damage, and quite likely the feed pump will collapse within a short time. While still operating in this condition, the liquid fed into the high-pressure pump most likely contains harmful gas bubbles that again reduce the performance of the high-pressure pump. Now, let's take a look at different kinds of centrifugal pumps and their properties as feed pumps. As you can, the single-stage centrifugal pump has the highest NPSHR values and the highest incline in the high-flow end. The incline indicates a high probability for high-flow cavitation. Multi-stage pumps perform much better, especially when they are equipped with low NPSHR option. The NSPHR net suction positive head required in multi-stage pumps is lower, and the pumps can be used in larger flow areas before cavitation occurs. Based on this analysis, our recommendation is the following. Be careful in your selection of the feed pump. Multi-stage pumps should be your preferred choice in order to reduce the risk of cavitation in the high-pressure pump. Be careful in the way you operate the pump. Ensure safe pressure and flow levels to prevent gas bubbles that may cause cavitation. This may sound like a costly approach, but it pays off in the longer term. It protects both feed pump and high-pressure pump and reduces the operational cost of the entire system. It is now time to troubleshoot your system to avoid cavitation damage to the high-pressure pump. If you suspect risk of cavitation in the high-pressure pump, first, check the high-pressure pump itself. Check if the inlet pressure, shaft speed, and temperature are within the specified limits of the pump type. If these values are okay, you should start looking for other causes. First, check if the centrifugal pump feeds gas bubbles into the feed water. If the feed pump runs at its maximum flow settings, it is likely to create gas bubbles. Check feed pump inlet pressure and check for vortex in the water tank. If you operate a two-pump system, where one of the pumps is a backup pump, we recommend that you redesign the system and mount VFD on both pumps. This allows you to operate both pumps at the best efficiency point with low risk of cavitation. Here, you can see an example of a two-pump system redesigned with VFDs on both pumps. VFD ensures that the two feed pumps never run at maximum flow. They share the load and both operate at maximum flow conditions. This will reduce the shaft speed and eliminate the risk of cavitation. Another benefit of VFD is energy savings. VFD allows the pump system to deliver the required feed pressure and only that at all times. What happens if one of the pumps fails? The next slide will explain. Column 1 shows the normal operational mode, whereas column 2 illustrates what happens if one of the pumps fails. The two pumps, in this example, are running full flow, and the flow is split between the two pumps. As soon as one pump fails, the remaining pump will speed up and take the full load and run up to maximum speed. This acceleration brings the pump to maximum flow and thereby cavitation point. It is obvious that the failing pump has to be replaced or repaired as soon as possible in order to avoid cavitation damage to the high-pressure pump. To avoid this risk, you should consider using a three-pump system to achieve maximum reliability. This solution is illustrated in the next couple of slides. Now it is time to see some test installations that illustrate the problem of gas bubbles in the feed liquid. The tests have been performed with kind assistance from Danfoss, the world's leading producer of centrifugal pumps. The test was made with a multi-stage pump with throttle valves on the inlet and outlet of the pump, which allowed us to control the pump inlet pressure and point of operation. We mounted a glass tube on the outlet so that we could observe the gas bubbles released from the pump. It is important to keep in mind that the test results were achieved using a multi-stage pump, whereas a single-stage pump would likely deliver a much poorer performance. The first test shows what happens if the inlet pressure is insufficient. By throttling the valve in the inlet of the centrifugal pump, the available pressure, NPSHA, is lowered to a critical point where the pump starts to cavitate. As seen in the video, a high amount of gas bubbles is released into the outlet water that feeds into the high-pressure pump. The next test shows what happens when the outlet throttle valve is opened and the pump flow is increased. As soon as the flow approaches the pump's maximum capacity, gas bubbles start to form. This indicates that the pump is about to cavitate. There are no defined points marking the starting point of the high-flow cavitation. It is a gradual transition. The final test simulates what happens if gas comes into the pump inlet, for instance, caused by vortex in the water tank or leaky joints or seals. Air entrainment can occur if the pump inlet pressure is below atmospheric pressure, typically due to the shaft seals. If you need to check for air entrainment, here is what you need to do. First, check for vortex at low water level in the tank. Second, check if splashes from the water inlet generate air bubbles that enter the pump, both at high and low water levels in the tank. And finally, check all connections on the inlet side of the pumps for leakages. First, check for visible leakages when the pump is turned on. Then, turn the system on and check shaft seals by spraying soap water onto the seals and connections that could potentially cause the problems. It can be very difficult to detect gas bubbles in the feed water for the high-pressure pump. A sight glass on the feed pump and the high-pressure pump skid is the best way to detect the bubbles. The pressure gauges on the feed pump skid can also reveal potential problems. Observe the pressure gauges on the slide. The left one has a stable needle, which means that the operation is safe. The right one fluctuates, which indicates that the pump releases gas bubbles into the water. If the high-pressure pump fails due to cavitation before the scheduled service inspection, check inlet pressure and temperature. If these values are within limits, compare the pistons of the defect pump to the other pumps in the system. If the wear of the piston slippers exceeds expectations, open the pump and look for cavitation damage inside the pump. If you find cavitation, it has most likely been caused by gas bubbles released by the feed pumps. It is time for some conclusions. First of all, consider the feed pumps that you are using. Single-stage pumps should not be the first choice, since they can cause cavitation damage if they are operated outside the best performance point. Go for multi-stage feed pumps with low NPSHR values to be on the safe side. If one of your high-pressure pumps fails due to cavitation before the scheduled inspection, take action fast and investigate the cause immediately. Check inlet pressure and temperature on the high-pressure skid. If the data is acceptable, find out if gas bubbles are fed into the system from the feed pumps. If you determine that the high-pressure pumps are damaged by the feed pump water, investigate the operation of the feed pump. If the feed pump runs close to its maximum flow capacity, you are likely to have found the cause of the gas bubbles. In this case, you need to switch the feed pump to a multi-stage pump, preferably with VFD. If you mount a sight glass in the feed water inlet of the high-pressure pump skids, you can easily detect gas bubbles. We recommend that you install the sight glass in a bypass loop to keep the cost low and allow easy replacement without system downtime.